last video we were working with a set of parametric equations, and we came up with this picture right here that went along for our interval from t equals 0 to 4. One thing our textbook author will ask us is say, look at that, and I went to Desmos to draw that same sketch that we just did. And one of the questions that he asks on this problem is sketch a graph of y equals 3 minus x squared. Y equals 3, I'm going to turn this off, minus x squared. And it says compare them and see how they're different and how they're the same. Okay. Notice, I don't know if I can get this one to be on top. Of course I can't. Okay. That the red graph and the purple graph are the same graph. It's just that the purple one is only a segment, okay, of the red graph. One thing that we will be asked to do sometimes is when we're given a set of parametric equations, someone might say, well, I want to know what equation that is with just x's and y's. I want to get rid of the t's, and we call that eliminating the parameter. Let's see if I can type that small here. We want to eliminate the parameter. When we eliminate the parameter, again, that means we're only writing it in terms of x's and y's. And there's more than one approach we can take, but the one we'll use most often is to use substitution. Okay, we think of this as a system of equations because it's really pretty much what it is. Okay, I've got two equations and I've got three variables, but I want to get rid of one. So if I look, and we can do this with either variable, x or y. But if I look at x equals square root of t, if I want to solve this for t, I can square both sides and say, well, t is equal to x squared. Then when I come over to the y equation, y equals 3 minus t, I can replace the t with the x squared I found. And I can say, well, y equals 3 minus x squared, which we've already seen with our eyes is the same graph, same shape as that purple graph, okay, our blue one here. Now, the thing we have to be careful of is if I just gave somebody this equation here, they would think we would have that whole red graph from the Desmos worksheet and not just this little piece, which is the only little fragment that I want, segment, that I want from here. So we need to restrict the domain and say, and from our table we've already found this. We said, well, x's are only going between 0 and 2. Okay, that's the only piece of the graph that we want. If we want to eliminate the parameter over here, okay, when we have sines and cosines, when we make up a new problem, we erase it. And when we're dealing with sines and cosines, then we're still going to do a substitution, kind of a variety or theme and variations on that. Okay, but what I'm not going to do is try to solve one of these equations for theta. I could over here say theta is the arc sine of y over 2, or I would have to divide by 4 and then take the square root and then have the plus or minus and then do the arc cosine, and that looks like a big old mess. So more often, when we're looking at our trig functions, we are going to think back to those identities that we worked with in the last chapter. And I'm always going to think about Pythagorean identities if I can. Now the nice thing about this x is it already has a cosine squared theta in it. And so I say, well, I can make a sine squared by squaring both sides. And fortunately for me, I'm going to end up with a 4 out in front. I like this coefficient to be the same. If it's not, I'm going to have more work to do. But a lot of the situations that you're given in our book don't require a whole lot of maneuvering. So notice if I take the x from straight above me and I add that to y squared, then I have 4 times cosine squared theta plus 4 times sine squared theta. And if I factor the 4 out, a lot of you took a longer path on this on your test, and it wasn't incorrect. It's not wrong to take a longer path. But oops, I don't know why I did that. But I would like to point out that if you factor out the 4 here, cosine squared theta plus sine squared theta is equal to 1. So this looks like x plus y squared equals 1. Now, if we wanted to solve this for y, it would be a mess. So we're not going to go all the way down to y, but we could say y squared equals 1 minus x, and making up new problems. Y squared equals 1 minus x. We could solve it for x and write it as a function of y. X equals 1 minus y squared. Okay, any version of this. And if I sketch a graph, maybe I'll just write in x plus y squared equals 1 because Desmos doesn't care. Okay, here's the little piece that matches, hopefully matches, what we had here in our blue graph that was a much more raw sketch. Okay, but we said x plus y squared equals 1. That's not what we said. X plus y squared equals 1. And it doesn't equal 1, so tell me what I did wrong. So Mr. Jackson in here is equal to 1, but you forgot to take it times the 4 because you're in a hurry again. So let's change this to a 4, and then notice how it lines up the way we need it to. All right. Now, if we needed to restrict the domain here, we would have to tell them, here is our values of theta, but we can't, if I say, well, theta goes between negative pi over 2 and pi over 2, and people would look at these three situations and say, I don't see no theta there, Ms. Jackson. I think you've lost your mind. So we need to either tell people that x, we need to either restrict the x's. Oh, look, x goes from 0 to 0. That doesn't make sense. We could, if we just look at our starting and ending, we could say x equals 0 to 4. Okay. Write it in a way we can read it because our x values go from 0 to 4. We could tell them restrictions on the y. Y goes from, looks like the lowest end is -2 to +2. Okay. And again, you don't have to tell both. You just have to give one restriction or the other. So either tell them the limits on the x's or tell them the limit on the y's, them meaning me or whoever the reader is. Okay. And then they'll know that you're only looking at this piece right here and not the entire blue graph. If we restrict the x's, here we go. And I forget how to do that here in Desmos. There's a way, but I always have to Google it. If we go clear back to the beginning here to our first example that we started with in the last video, let's say instead of being told this equation up here, we'll say, well, this goes along with x equals 4 minus 1/2 t. Okay. And y equals 2t minus 1/4 t squared. I want you here in just a moment. Let's let our t's go from 0 to 8. Okay, so I want you to pick some values. When I say pick, I'm going to pick them. Let's do 0, 2, 4, 6, and 8. Okay. Find me the x coordinates, find me the y coordinates. Oh, I was doing so well. Okay, and plot those points on the graph, and then be sure to draw your orientation on that graph. When you come back, I'll have the table filled in and the graph made. We'll talk orientation together. When x is 0, 2, 4, 6, or 8, we get those values for x, and 0, 3, 4, 3, 0 for y. Now when t equals 0, we're starting over here at 4, 0, and then we're moving our way. I'm going to have to connect my dots left to right if I'm going to have any sort of decency to that shape. Okay, but when we put our arrows on there, understand that we started here on the right and went back up and back. So if I was kicking my soccer ball, I started here and I kicked it back toward the origin instead of maybe the way I described the graph in the first video where I said maybe I'm kicking the ball this direction. Okay, the orientation comes from as my t increases, which way is my graph moving around on the page. Notice if we wanted to eliminate the parameter here, maybe I want a different color so I don't make a mess. Okay, again, pretend I didn't know this. Go ahead and solve the top equation for t, because it would be a big mess to solve this one for t. So solve the top one for t, plug it in down here, clean up what you have, and see if it matches that. I'm going to pause. We solve for t, here we are. When we plug it in to y, and we FOIL and we distribute, we get this. And if we say, well, that doesn't look like what I have up here, I'm going to tell you it's the same thing. Okay, I'm going to leave you on your own to verify that. But if you FOIL this on the right side, distribute the negative, combine your like terms, you're here. Or if you complete the square on this one after factoring out the negative to put it into our vertex formula, you'll be there. Okay, so check that on your own. Let me know if you need help eliminating parameters.